In this video, I introduce matching, normalizing flows, and probability path on manifolds. Continuous normalizing flows are generative models that transfer a simple prior distribution to a model distribution by solving ordinary differential equation. CNFs on manifolds are trained by minimizing probability path divergence between the probability density path generated by the CNF and the target probability density path. Given a time-dependent vector field V, the continuous normalizing flow phi t is defined via the ordinary differential equation as shown here. For a probability density, the pushed forward by phi t is defined as here, and the pushed backward is defined as here. A probability path P is smooth in T and satisfies this equation. Phi t generates a probability density path Q if for all t between 0 and 1, as shown here. This pushed forward equation and this pushed backward equation. The goal is to match the density path Q generated by phi t from the prior P0 and the target probability density path P. The CNF matching can be defined as the following optimization problem as shown here, where D is the probability divergence between probability density paths P and Q. PPD doesn't require sampling of Q or enforcing equation above explicitly, and therefore sidesteps the need for solving ordinary differential equation during training. A partial differential equation is derived to construct a PPD involving a log density path and vector field V, such that it is satisfied if and only if phi t defined by V generates P. Consider phi t defined by a smooth time-dependent vector field V and the probability density path P. The path P is generated by phi t using the following equation as shown here. If and only if the logarithmic mass conversation holds over between 0 and 1, namely this equation, which is equivalent to continuity equation as shown here. Plug in a fixed target path B in the LMC equation provides a necessary and sufficient condition for V to generate P via phi. A formula for PPDs is defined and parameterized by integer L as shown here, where T sampled from a uniform distribution U, and D, L larger and equal or equal to 0, and DL is equal to 0 only and if PT is same as QT for all T between 0 and 1. Use this path divergence in the CNF match, we have this minimum problem, where the learned V is used to compute phi t, and then phi t is used to compute path Q. Existing CNF approaches applied to optimize CNF matching and requires evaluating Qt through solution to ordinary differential equation at each iteration, which introduce substantial computational cost. Instead, PPD doesn't require sampling of Q or enforcing this equation explicitly, and therefore sidesteps the need for solving ordinary differential equation during training. Consider path P and Q, where Q is generated by phi t, and Q0 is same as P0 for all t between 0 and 1. We have this bounded equation, where df calculated from this integral, and ft takes 3 formulations in 3 conditions. The target path P satisfies the following requirements. P0 is a pure noise. For example, standard Gaussian or uniform distribution. P1 approximates the unknown data distribution P data. We have an efficient generation procedure for X sampled from PT. We have an approximation procedure for the time and space derivative of log PT. The target P is computed by using this formulation, where tau is a time-dependent scale function and gamma is differentiable in T-map. In practice, P data is unknown. However, empirical sample yi is drawing from P data. Therefore, PT is approximated as shown here. If we know how to compute or approximate log P tau, then log PT required for computation of the PPD has the form as shown here. The target path constructions depend on the type of manifold. For a unit model, prior assume that O is a designated point. Sigma 0 and sigma 1 are initial and target scales. The path and P is computed by selecting in this formulation. And sigma T is calculated from sigma 0 and sigma 1, where tau is a scaling function. Gamma T moves y to the center O along a geodesic. With these choices, PT starts with a single model density P0 centered at O and then splits the unit mass, moving each 1/m part towards the empirical sample yi along the geodesic while concentrating the density. For a Gaussian kernel, P tau sampled from a normal distribution with a mean y and covariance. Gamma T is expressed as here. Therefore, PT is computed by using this equation. Takes sigma 0 is equal to y, represent a standard Gaussian prior, namely sigma T calculated from tau 1, sigma 1, and sigma 1 is the only hyperparameter. For more details, please check with these references. Thank you. Bye.